Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. My guest is person.Mola. He's the founder, president, and CEO of Roswell Biotech. The website is roswellbiotech.com. So, Paul, how you doing? Thank you for coming.
It's a pleasure. It's absolutely great to be here to talk to you guys about Roswell. Thank you.
Yeah, tell me, what's the Roswell reminds me of aliens and Area 51. Where did the name come from, and what's the premise of the company?
The name really comes from the fact that we are an emerging technology. If you think about it, at the outer edges of what is possible, we are taking molecules and integrating them into nanocircuits and making them part of the circuit, which is pretty much an out of this world sort of idea that seemed to be very alien. And so for us, it was simpler to tell people that the technology and inspiration came from outer space or from aliens, and try to explain it. And that's the genesis of the name.
What's the premise of the company, though? It's like, what are you guys working on?
So we come from, myself and my co-founder Barry Merriman. We come from the sort of genomics field, and we have been very passionate to drive application of genomics technologies to solve disease. And having been around the block, both from a technology development side of things, but also from a practitioner, where we are, worked with governments and large entities to actually catalog and sequence genomes in the millions of genomes, we realized that the technology was just not ready to actually be undertaking these population scale projects. And so the idea is that if you think about precision medicine and wanting precision medicine to be a reality, we need to go out there and sequence genomes at scale to create a knowledge base, then which becomes the foundation from which we can start to interpret and understand what the genome is. And so we after we went out there and tried to execute these projects and realizing the technology wasn't ready, we went back to the drawing board, and sudden sort of advancements in technologies in nanofabrication, in CMOS fabrication, made it possible now to approach the technology from a different perspective, where we can actually drive some very drastic sort of specifications, primarily around the cost to sequence the genome, and secondly, around the simplicity and turnaround time, such that these devices we are making can be deployed at a doctor's office and allow the doctor to very simply, because of a simple workflow, run and sort of analyze a genome relatively quickly and cheaply, and make that then sort of drive then at least make the genome just be part of that medical record and medical practice. So just to summarize again, that what we're about is revolutionizing our ability to read the genome in a way that we're going to make it democratize that and make it available then for people as you go to your doctor's office to have that as a part of your record.
Well, even if you did that, I don't know if the doctors would know what to do with it at this point. I mean, if magically we could do that today, what would the doctors do, or is that part still lagging?
You are absolutely correct. That part is still lagging, and it's a bit of a chicken and egg problem. And the issue which you're highlighting is that if I were to sequence you today, the utility of your genome is very little because we don't understand a lot about it. And the way you solve that is that you essentially need to create this genomic encyclopedia, where if I see a mutant or a given variation in your genome, I can go look it up, and then the encyclopedia will tell me exactly what's the problem, what are the potential medications, what other therapies are available. And we do not have that encyclopedia today. It does not exist. There's a very, very, just a few chapters of it have been written versus volumes. And the way we write the encyclopedia is we need to sequence genomes at scale. And by sequencing many people and stratifying these people into, diseased versus normal category, into males versus female, into different age groups, then we are able to start to see the patterns that cause disease, and we are able to start to drill down to the very specific changes in the genome that result in a given phenotype. And so why we do not have that encyclopedia today is because it actually costs, about $1,000 to $1,500 to sequence one genome. And the problem is that the insurance company won't pay for it because the utility does not exist today. And the way you solve it, hence the chicken and egg problem, is we need to go then and find a way to fund creation of this encyclopedia, which means it is all about cost. And so we're going to drive down cost. And by doing that, we'll unlock all these studies and sequencing of populations where a government or a large entity can just pay for it to create a foundational knowledge base. And so that's where we feel that our step one is going to be to unlock these large population initiatives. There's the Genome England, there's the Cancer Moonshot in the USA, there's the Million Veteran Program, for example. So all these programs have samples just queued up and ready to be sequenced. And we'll be able to unlock that and start then the process of creating these knowledge bases that then get leveraged for precision medicine in the future.
So what types of things are people seeing already from sequencing genomes? Is anyone sitting on a database of even 1,000 people sequenced or 10,000 people, and what are they saying?
Yeah, there are such efforts. Human Longevity, for example, here in San Diego, Nant Health up in LA. There's various initiatives. There's the Saudi Genome Project. There's the Genome England Project. I think the one that I like to highlight is the Saudi Genome Project. And what they did there is they went in and sequenced not the full genome, but as part of the genome, which we call the exome. It is about 10% of the genome, and represents the part of the genome that expresses proteins. And they sequenced that for their population. The net result is they created a catalog of information about variants that are specific to their sort of country. And what they've done now is in Saudi Arabia, before a couple gets married, they are required to take this, or they are required to take this test that is going to assess these variants in the potential couple. And they get a report that tells them, hey, if you guys are going to have children, it's highly likely that you'll have a child who's got X or Y or Z, and they're counseled, and then they have an option to either proceed to marry or not. And they've actually been able to drive incidences of some diseases in the region by almost 50%, just because of decisions to not get married and have children, for example. So, that is one example. And on a sort of, if you look at just some of the diseases out there, you can look for example, single point mutation diseases, right, which result in genetic diseases of various sorts. You are looking at, if you consider cancer and cancer therapy, there are markers that have been identified that can actually help to inform therapy. So yes, this is being used today, and I think it's just a drop in the ocean as far as the potential then to take this to the next level by even creating more robust knowledge and to drive this forward.
So what's going to be required to get sequencing below the $1,000 threshold?
Well, it is. If you look at the current sequencing technologies today, I mean, if the current market leader has been at this almost 2 decades of really incremental improvement of their foundational technology. There's other approaches in the market that really have persisted for at least 2 or 3 decades. what Roswell is bringing to the table is think of it as a step change technology in creating a biosensor. And so because what we are doing is we are marrying CMOS technology, and CMOS technology is really the technology that is used to make the chips in your computer or in your phone. These chips are manufactured using very advanced factories or foundries. There's trillions of dollars of investments that have gone into these foundries. And the beauty of CMOS is the ability to integrate into a very small chip, very powerful sort of capability. And so CMOS itself is a nanotechnology. And so what Roswell is doing is that we've found a way to essentially develop what we call it's a nanochemistry that then is compatible with a CMOS chip. And if you marry these two, then you provide a very powerful platform that can actually scale. And CMOS is a very scalable technology, and having a chemistry that scales with CMOS then opens up a whole new world in the world of biosensing. And so the idea is that we are taking the enzyme that actually in nature makes DNA or makes a copy of DNA, and then we are using that enzyme essentially to make a photocopy of a piece of DNA. And then as it makes this copy, we are actually able to eavesdrop and monitor the enzyme electronically and very, very directly. And so when you take the enzyme, the polymerase, you integrate it into these nanocircuits, and then as the enzyme starts to do what it does in nature, it starts to send out these signals, and and that's how we actually read. And so the idea then is because of the technology platform and the scalability and the cost of that platform, primarily being on CMOS, it allows us then to start to approach these cost basis and performance that was previously actually just a dream and not possible. And so for us, the $100 genome is really a starting point. We see a roadmap to getting to $10 genomes. Right now it is a $100 1-hour genome is what we are targeting, but with a roadmap that goes to $10 10-minute genome. And that's where we feel that then we have the specifications that can unlock this precision medicine market and really change the way we practice medicine today.
And right now it's $1,000, and how long does it take on average?
On average, it just takes about 24 hours and about $1,000. Other key point to note is that the technologies currently being used today to sequence a genome, these are about $1 million a piece. And so if you think about that, just the cost of getting the instrumentation and the platform into a lab is mostly cost prohibitive. And then running it then is the other problem where you have to then, it's about $1,000 to run it and get a result. And so the idea here is that it does not need to be $1 million instrument, right? It needs to be, in the tens of thousands of dollars to get that instrument at the doctor's office or in the clinic or in a lab. And then it shouldn't be too much to run per genome. So we are trying to revolutionize it from multiple angles as well. And it's not just the cost per genome, but it's the entire sort of ecosystem to run and operate such systems.
So you're going to try to maybe do several different sequencings in parallel to do it faster, or how would you do it faster, and how would you do it, so much? Well, I guess we'll just talk about the faster part.
Yeah, it's exactly. So we're not playing the game of actually just, like having, what we'll do is we'll have a single chip that every chip will give you a genome. And that chip is going to be tuned with the appropriate features so that when you run it for 1 hour, then you actually get your genome. And there'll be other systems, of course, in the future that we'll consider that are going to be more for a factory type setting where you can, run multiple chips and get multiple genomes at a time. And so we are considering both approaches.
Well, how are genomes sequenced right now, according to your understanding? Like literally, what are some of the details of what happens?
Well, the way genomes are sequenced right now is It's the same way if you were to take, say, a page from a book and you wanted to make a photocopy of the book. There's two ways to do it, right? One is I can sort of take an image of the whole book and copy it the way it's done today. Or if you had very sort of archaic technologies, you could think of an approach where you're copying one letter at a time, which takes a lot more time to do, introduces more errors because of just the way that technology works. So today, the technology is akin to copying one letter at a time. And essentially, the instruments, the way they do it is they sort of copy one letter, and then they pause. They have to then wash everything again off from the system, and then introduce then the next letter. Then they read the next letter, wash, clean up, and then read the next one, and so on, until you've read your 3 billion letters of the human genome. In our case, we actually do not do it that way. Our system is more like we photocopy the whole page at a time. And this is about when you think about read length and that sort of thing, or if you think about the way we are sequencing by having, it's like real-time sequencing where we do not need to do these stop and washes. And these stop and washes are what add up a lot of time and require, that's why it's 24 hours plus to sequence today. And with every step of this other system's approach, because you have to wash off and reintroduce new reagents and new materials, it's essentially very wasteful. And so it's wasteful, it's slow, and it's also cumbersome and creates for a very complex technology because of the way they sequence. In our case, we introduce all the reagents in solution, and when we hit go, then the enzyme just runs through the genome and reads the whole thing, and in the process makes a copy of it without needing to stop it sort of artificially between each letter that is read.
Yeah, that sounds like a lot faster. And then offline, essentially, you could process things like extremely quickly with computers.
Yes, exactly. And that's all about the sensor. The way that it is currently done, just to go a little bit more into the technology, and I can go as deep as you want, but the way it's done today, the genome has 4 letters, right? So you have your A, G, C, or T. And each of these letters has a different sort of dye associated with it. And what they do is you take a template, which means you have the page that you want to photocopy, and then I'm going to flow in one letter at a time and see whether this letter actually is the letter, right? So if I flow in an A, for example, and the letter that I'm looking for is a G, the A will sort of just not stick, and then I have to wash it off. Then I flow in a G, and then if the G sticks, then what I do is I actually take a picture. And when I take a picture, I'm going to see then, oh wow, okay, that's green. That means that is actually a G. And then I say, fine, now let's wash off the G and cleave off this dye and then introduce the next one. And so it's very, the technology is really just, we've sort of been forced to adopt this technology in a very unnatural way, with the way the enzyme works. I have to stop it between the reads. I have to then take a picture and then wash it. So it's slow, it's laborious, it's not as sleek. And versus saying, you know what, let's just load up all the reagents. I do not need any fluorophores. I'm going to use natural bases, A, G, C, T, and then when I leave it in there, the enzyme just starts to work, and I'm monitoring it in real time. And then those are the signals I get out of it, which are all digital and electronic versus optical images that I need to take.
I guess at least as an early stopgap, it sounds like you should run 4 different preparations, one for each base pair, and then you'd have to wash it maybe not at all or less frequently. Do one for A, one for C, one G, one T, or would that not work?
Yeah, no, it literally does need that. The way it works is it has to, if you don't have a compatible letter, I still need to take a picture, and I'm going to see dark, which means I don't have a letter, and then I have to wash all that stuff off and then go to the next one. There's no way of skipping, and I have to do everything very sequentially, one at a time.
Oh, okay, I gotcha. Okay.
Yeah.
So where are you at with your process? How long until you're able to start doing it?
Well, so we've made a lot of progress at Roswell. The first year of our operations, we just spent really figuring out how to nanofabricate these devices. We are at the bleeding edge of technology, and the ability to make very, very small circuits that approach the size of the molecule itself. And so we've made those. We've taken that chemistry and have successfully now deployed it on these CMOS chips that we've made out of the world's leading fab in Taiwan. And now we're in a place where we're really working to optimize the chemistry on chip, and then start to tune the read length and accuracy and that sort of thing. So we are anticipating to get to early access with thought leaders in about the 18 to 24 month time frame, which then is going to be the sort of trigger to go commercial.
Okay.
Yeah.
What's your timeline? Do you think it's going to be maybe another few months or a year, or when do you think there's going to be the first leap forward where you have your prototypes running and evaluating?
So we do have internal prototypes running now. So we're really looking 2020 to start to engage the thought leader market and the broader market in the 2020 Q3, Q4 timeframe.
Okay, well, that's not too far away.
Yeah, we have a work cut out for us.
Well, when you do this, again, what are some of the first things that you want to look at in aggregate when you're looking at DNA of many, many people?
You ask a good question, and the way we're developing this technology is we want to read the DNA or the genome in a very comprehensive manner, right? So, for example, traditionally when we read the genome, as you know, right, we have if you look at humans, right, we inherit one set of genes from our parents, one set of genes from the mother or from the father, and we are not even at a place where we need to understand what came from the father, what came from the mother, so we have to phase this genome. Two is we need to be able to actually look at the epigenetic changes in the genome, so it's not just the AGTC, but I'm going to look for other modifications which actually start to tell me more about how these genes are regulated. And then we just need to sequence them at really long read lengths, which means I'm actually going to be able to get more better context and coverage of the genome. And so today, the way we sequence the genome is not at all sufficient for these reasons I've told you, and we are solving for that. And it's just a question of then which are the diseases that we want to target first, or which are the populations we want to target first. There's quite a few samples that have been curated by different initiatives, like I mentioned some of them, the Cancer Moonshot project here, or the Genome England or Scottish Foundation project, the Million Veteran Project. We'll go to the Duchenne Foundation, for example, and look at those samples. So we'll target samples that have been well curated, and that means they have the other information that is not genomic, and it's just needing the genomic information then to pull it all together. And then we'll partner with those entities to start to at least drive creation of the knowledge base. That's going to be our initial focus before focusing then just on sort of individual genomes that just to. So I guess the past point is yes. Let's do the population scales and let's see how we can actually facilitate or catalyze that effort in various countries. And then following that, then you have better utility of the genome, and that's probably going to be about a 3 to 5 year process before you start realizing back then the utility of that information.
What about the privacy of the data, though? In the U.S. you have HIPAA laws, and do you expect that you'll actually be able to not just be a provider of these, this technology, but actually see the data results, or is that all going to be siloed immediately? Per person or per doctor's office or, per company?
Yeah, I've seen various sort of business models to approach this, and both of those are available, right? Just for example, there's many of these samples which are already curated. This is, disease consortiums that have pulled together the people who need help the most, and these disease consortiums then have taken the right steps to consent these samples, and so these are just ready to go. And the sequencing will be done under those frameworks, and there's then the right framework where the analysis of the results can be done and results provided, or otherwise we will just provide the genomic information back to these entities, and they will then be able to make sense of them. There's the other then sort of business models that we've seen emerge where they will pay to sequence your genome, but then you will sign rights to the data, where they can then work with pharma companies and biotechs to then try to understand and mine that information for then therapies and druggable targets and that sort of thing. So it's still, I think at the end of the day is that we need to find a way that we are going to be able to provide our genomic information under a certain framework so that we can pull it all together and learn as much from it, because we are not going to be able to learn just from looking at my genome alone. I have to look at it in the context of other people. And so those are the frameworks that have not completely emerged, but I think we know that there's the world sort of warming up to that, right? If you think about what 23andMe has done, there's quite a few people who've sent in their samples to be sequenced, and it's good because they can then go back and look at, what has changed since I looked at my results, because maybe there's been a new discovery and it has been applied to my sequence, and this is what it means. And so I think we're moving to that world. And yes, privacy remains a concern, but it's more about can one use genomic information to discriminate? Because maybe I have a disease and I don't want my insurance company to penalize me for that. And I think that you can take care of by the appropriate laws, versus having that be a limitation for sharing and learning from each other's genomes. So that's kind of the way I will look at it.
Do you think that this will be something doable at home, where you'll be able to go to the store or just order a kit and run it at home for yourself? Or is that another level of complexity?
No, I think if in 10 years' time, absolutely. I think there's going to be a time where kids will be running genome sequencing experiments in schools. At home, you'll be able to just sequence, your child or your sample to see whether you have an infection. So I think those yes. So I think it's coming, and it's going to be, especially in the world where you have your cell phone integrated into all these other databases and knowledge bases, that it will make sense that you're able to do it at home. And then also from a cost perspective, it should be very, very affordable to do a simple $10 test at home and throw it away, just like you do, like, I don't know, a pregnancy test or something.
Yeah, and the laws are going to have to evolve too, because you certainly don't want gene-based discrimination in any form, or the data needs to be kept private, because it could open someone up to vulnerabilities that would be unique to them.
That is right. Yes, the laws will need to catch up, but the technology is moving probably faster than the laws. But I believe there's already a law that was passed against genetic discrimination. But I think with time we will even see more laws that are going to provide the protection to allow us to generate this knowledge and share it and learn from each other in a way that is safe and not in a way that doesn't discriminate.
Well, very good. I mean, it's amazing stuff you're working on, and I appreciate you coming. So what are some resources for listeners? How can they find out more, maybe reach out for collaboration or ideas?
Yeah, I think our website is a good starting point. We do talk about the technology, and we are continuing to build a website. There's going to be more information on the website.
You've been listening to Almost Here, Around the Corner of Future Technology podcast with Richard Jacobs.
Continue to do interviews.
Subscribe to this podcast, post a review, to discover more future technologies
on the website
that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality.
Very good. Well, Paul, I appreciate you coming on the podcast. Thank you so much.
You're most welcome. Thanks for having us.